Okay, good morning. I was asked to summarize the linear collider R&D in the U.S., and I sort of took as my implicit charge to create the impression that we have a coherent program. And I will try to create that impression, but I'll also try to give you enough information that you can make your own judgment at the end. I'd also like to give you enough information that you can really understand sort of what some of the outstanding remaining issues are, and perhaps these actually contemplate whether you might like to get engaged in any of that. So this is the outline of my talk. Goals, sort of the generic R&D program elements, and I'll talk specifically about NLC activities in the U.S., Tesla activities in the U.S. Just one slide, because I don't have much time, on site studies that are going on, and then sort of my view of what some of the remaining technical challenges are. Okay, I always like to start with goals. What are we trying to accomplish, and formulate these goals within a context, which I've written here, which we all know. We've heard this several times in this workshop. The directors of the U.S. labs have publicly stated their support for the construction of a linear collider as an international endeavor based on the optimum technology. And this vision has been further supported now by the HEPAP subpanel and its European and Asian counterparts. So within that context, I think the goals of the U.S. R&D program are to develop the technology that would support construction of a linear collider operating at an initial energy of 500 GeV and a luminosity of at least 10 to the 34, and upgradable to an energy of in excess of 1 TeV. The bulk of the U.S. effort, as I think you all know, right now is currently directed into X-band, an X-band-based implementation. But however, both technologies are aiming for demonstration projects and a decision on the time scale of 2003 or 4. Okay, just to sort of remind you what the parameters are, I compiled this list. It's got 3 columns. This is the NLC and the JLC X-band column, which of course are very similar, and so I've actually just listed the NLC parameters. The JLC parameters are essentially the same. For your information, this is the C-band implementation of the JLC, and then here are the Tesla parameters. Again, as I said, these are all written at 500 GeV. In this case, they deliver luminosities in excess of 10 to the 34. And the primary difference one sees in these, of course, has to do with the way the luminosity is packaged. In the NLC, the X-band case, there's not a very long pulse length. There's 190 bunches separated by 1.4 nanoseconds, whereas in the Tesla case, there's close to 3,000 bunches separated by 300 nanoseconds. Okay, so what are the elements of an R&D program that are required to enable achievement of any of the parameters in that chart? Well, I've grouped them into a number of categories. Let me start with energy performance. Energy, achieving the energy is based on 2 things. One is RF structures, and the second is RF power generation and delivery. The structures themselves, either effort must develop an accelerating structure that supports, thank you, Mark, supports the desired gradient in an operational setting, and there must be a cost-effective means to manufacture, fabricate this structure. I'll get back to this somewhat later. With the RF power generation and delivery, the generation and distribution system must be capable of course, getting the power to the structure that's capable of, that's required to support the design gradient. And there are a number of demonstration projects underway which are associated with demonstrating this sort of performance. In the X-band case, there's the NLC 8-pack test, which I'll say a little more about later. And in the Tesla case, there's TTF2, which I won't say as much about, but you heard a little more about that from the previous speaker. Okay, in addition to energy, you, of course, have to generate luminosity, and the generation of luminosity requires producing beams with the specified beam densities, that is positrons or electrons per bunch over emittance in an injector system, preserving that emittance through the LINAC, and then finally maintaining the beams in collision at the interaction region. And there are a lot of issues that come in here. Damping ring performance, which we just heard a long discussion on. There's vibration specifications and site characterizations. There's wake field suppressions in the LINAC compensation schemes for compensating for wake field effects, and then IR feedback schemes. And you heard about some of this on the first day. The R&D facilities associated with understanding these sorts of issues are listed here, and most of these, again, you heard about from the previous speaker. Links is an idea that's floating around at the moment, which, again, I'll mention very briefly later on. But these facilities were described by the previous speaker, and I won't spend a lot of time on those. Okay, a couple other things one has to worry about. One is energy upgrades. There's sort of been at least in this country, a continuous vision that there was a need to ultimately get beyond 500 GeV. So I reflect that here by saying there need to be at least a plausible vision when one embarks upon one of these projects of how to upgrade the energy to and beyond 1 TeV. Well, 800 GeV is the same as 1 to 1 significant figure somewhere down the road. And so this means we need to continue a program of gradient R&D to establish what the limits are on X-band structures and the superconducting structures. Sites, of course, one has to have at least one viable site identified and understood. And viable, again, I won't talk a lot about this aspect of this, but Maury talked a little bit about this the first day. It means not only technically viable, but there has to be public acceptance and support for whatever site we come up with. So this indicates a need to do site studies. Finally, the cost of the facility, both in terms of its construction and its operation, clearly is going to have to be understood. So those are the sort of the 5 sorts of elements that we think make up need to be addressed in an R&D program. Okay, so I'm going to switch now for about the next, I guess, probably 10 or so slides to the X-band program first. And what I tried to map out here is most of the elements that I talked about on the previous 2 slides, and who's involved. And while this talk says U.S. R&D, I did put K&K in here because there's a pretty strong coupling to K&K on the X-band program. And so what I've just indicated is who's doing what in this program here among SLAC, Fermilab, Berkeley, and Livermore. So we have, as you see, I think got pretty much all of these bases covered right here, and I'd like to start talking about those in a little more detail at this point. Okay, let's start with structures and gradient R&D in the NLC program. As most people know, it's been pretty well publicized. It was discovered a little more than a year ago that after some 1,000+ hours of operation in the NLC TA, the structures that were in there were starting to show deterioration. And this has triggered an aggressive R&D program that involves both what's represented here, which is the fabrication of a variety of cavities of different designs, and also what's not shown here, I don't have time to get into it, simulations and development of a theoretical understanding of what's going on. This sort of summarizes the situation at the moment. What's listed here are 4 different kinds of structures. This structure here, DDS3, is actually the original structure that showed the problem. It had been run up to a gradient of about 50 megavolts per meter and was exhibiting stable operation at 40. And to remind you, these are unloaded numbers, so the NLC spec in these units is 70 megavolts per meter. What's shown here is the nomenclature when you get into these test cavities. Here is T stands for traveling wave, 105 stands for, and I don't remember, it's either the length in centimeters or the number of cells. The cells are approximately a centimeter, so this is about 100, that's a meter long. Centimeters, 105 centimeters long. And the group velocity at the input to the structure as percentage of the speed of light. The fact that there's two numbers here represents the feeling that there were two relevant parameters. One is the length. The length sort of controls how much stored energy there is in the entire cavity. And the group velocity is telling you how fast the energy can get from point A to point B in the cavity. So you see, for example, first going down in length, going down in group velocity, a comparison between two cavities that have the same group velocity but different lengths. So energy can flow around as fast in these two cavities, but the stored energy in this cavity would be sort of half of what it is here. Okay, so this sort of shows the history, and this is actually in chronological order of what's gone out at the NLCTA test program. There's about 5,000 hours of high power operations out here, and it looks like this thing after a year is starting to converge on a solution that looks like it will meet the spec. This slide actually summarizes the operational history. This is sort of time on this axis. You can see there isn't really because it's not all scaled properly. But this shows the history of operations of these four cavities. Here was the original DDS structure that was at some point run up to close to 60, but was sort of at this point exhibiting damage. This was the shorter, lower group velocity, the somewhat longer, lower group velocity, not a big difference there. And then finally the one that's in right now, which you can see has been pushed up close to 90 megavolts per meter in processing and is running stably, pretty stably at about 70 megavolts per meter. This is a picture of that structure, and what's interesting about this is the diagnostics at the NLCTA is sufficient to isolate when a breakdown occurs where longitudinally in the structure does it occur, and this is an example of a 10-hour run at 70 megavolts per meter with a 400 nanosecond pulse length, showing that in general, in this all the breakdowns occurring either at the input coupler or at the output coupler. So this, of course, has prompted a next iteration, which is to refine the design of the input and output couplers. I'd summarize by saying at the moment it appears pretty likely that the next iteration of the NLC design will be based on a low group velocity structure of modest length, where modest length will either be somewhere in the range of 60 to 90 centimeters.
What compromises do you have to make when you're using low group velocity?
Well, the structures are shorter, and what happens is you end up with more input couplers basically on the whole machine. You're feeding RF power into it in a much more finely segmented manner.
Is that a big cost driver or not very significant?
Well, it's a cost driver to big. I don't know what the definition of big is. It is a cost driver. Okay, let me talk a little bit about the next issue, which is once you understand a design of a structure which works, how do you actually build them? The NLC will require about 11,000 structures if it ends up with a 90 centimeter structure to reach 500 GeV. We at Fermilab have undertaken the task of trying to develop an industrialization process for the fabrication of these items. The short-term goals we have are driven by the desire to initiate the 8-pack test, which I'll show you a picture of in a few slides, at SLAC in late 2003, early 2004. We've been developing a structures fabrication facility at Fermilab. We would like to assemble 18 90 centimeters, or if it's decided to go to 60 centimeters, 24-meter structures, which would include 12 or 18, depending on the length, destined for the 8-pack test at SLAC. And what we're shooting for is a capability of one structure per month by the end of this calendar year. Now, one can do the math here pretty quickly and realize that this is a long way from where someone has to be in order to build this machine, but it's a pretty big step up from what our capability is right now. So this is really just a step along the way. Tolerance is an acceptance criteria. We are trying to take the lead in developing a complete understanding of what the tolerances are on these structures. There's some uncertainty about that, and it's not real well documented, and then develop a QC criteria and specifications, which one has to do if one is actually entering into some sort of industrialization process. Finally, the girders that these structures sit upon, we're developing a girder design and going to prototype that this year. And ultimately, again, on this time scale here, we would like to deliver 2 complete girders with the structures sitting on them to SLAC for the 8-pack test. Okay, a couple words on status and some pictures. IB4 is Industrial Building 4 in our industrial complex. A piece of that building, which before we were there, housed the construction of the COT for CDF, is now being converted into a structures facility. This is being done with NICAD support. NICAD stands for the Northern Illinois Center for Accelerator and Detector Development. So I'll give a plug for them. That's centered at NIU University, one of the local universities here. And this particular furnace, so-called small furnace, if you go out there, you will find has a NICAD logo on it, because it was provided to us by them as part of their participation in our program. And there's a larger furnace which will really complete this facility, which will be delivered probably in about a month. With this facility, we have the first 20-cell structure. FXA 001 was completed at Fermilab last year, and FXA, our second structure, is nearing completion. Here's a picture of that particular structure. It's only a 20-centimeter long structure, but at least it's a start for us. So this is the first, I think, the first piece of electron linac ever built at Fermilab. Goals for FY02. Got to start somewhere. Okay. For FY02, the year we're in right now, we want to complete the fabrication facility. As I said, we think we'll pretty much be complete with the facility in March. And then there'll be a whole series of these structures we're going to test, build, and fabricate and test. As I said, the goal is to achieve a production rate of one per month by December of this year, complete the structures, QC, and acceptance criteria, identify vendors, which we are doing as we go through this, potential vendors and production techniques for another set, which would be presumably the final NLC design, and we'll also be prototyping support girders this year. Okay, so that's structures. Let me move on to power sources. The NLC requires about 2,000 klystrons, each capable of delivering 75 megawatts, a 3 microsecond pulse with a rep rate of 120 hertz. The status is that there has been this permanent magnet-focused klystron tube that you heard from Chris on the first day. 75 XP1 has been constructed and operated at 75 megawatts and 3 microseconds, although at a reduced repetition rate of 10 hertz. There's 3 more tubes in fabrication, one being built as a joint effort with CPI, klystron vendor out in Palo Alto. 8 tubes are required by the end of 2003 for this famous 8-pack test, which eventually you'll see a picture of. And that 8 is the same as that 8, as you might have surmised. Okay, modulators. You saw this picture also on Monday from Chris. It's about 250 modulators that are required, each capable of delivering 500 kilovolts, 3 microsecond pulse, again, 120 hertz. And the status is shown right here in this picture. There's this solid-state modulator based on these high-power switching technology. That development's being led by Livermore, and this particular unit has achieved again the 500 kilovolts in the 3 microseconds into this so-called 4-dog test. Although in this picture, I guess there's only 3 dogs here. Dog is a highly technical term for a klystron, which you will not use in the NLC.
It's a good dog.
It's a good dog, yeah. Okay, so what is this 8-pack test? The 8-pack test is envisioned by the X-band group as a proof of principle demonstration, the NLC RF generation and distribution system. The goals are, in this year we're in right now, it's what's called the single feed demonstration. This is to deliver RF power suitable to support 70 megawatt per meter unloaded for 1 girder's worth of structures. And once this is done, it will leave a test facility for RF power to be run independently of the high gradient structure testing, which is going on sort of next door out at SLAC. The second is to complete the 8-pack in late 2003. This would be the demonstration of the full power source with 1 DLDS arm. I'll tell you in a moment what a DLDS arm is. And demonstrate the full power operation of 2 girders, which is actually typo 10.8 meters worth of accelerating structures, including at least 1 girder of the final, what's regarded as the final RDDS structure design for the NLC. This is sort of the schematic that shows what some of those words mean. This is the basic building block of the NLC. Power source and distribution into the structures as envisioned at the moment. The DLDS refers to all these arms. What you do is you take 8 klystrons, putting out a pulse that's 3 microseconds long, and through the mysteries of RF engineering, you sort of slice and dice this thing up into a lot of little 400 nanosecond pulses and send them out all at the right time. It's basically a time of flight system where the RF, sliced pieces of RF are going this way, the beam's coming this way, and the beam and the RF is converging then on each one of these structures in time, so the beam actually gets accelerated. The single feed test really just means sending this amount of power into one of these structures. The 8-pack test is this piece right here. It has the full complement of 8 klystrons run by 1 modulator, which is not shown on here, going into these 2 girders worth of structures down here. So that's what that's aiming for. Okay, there are a lot of other areas of R&D that I really can't go into in much detail, but I wanted to list some of them right here. One has to do with the electron sources, electron polarization with thin strained lattices, work that's being done at SLAC in Nagoya. And the status of that is polarization is 78%. It's been measured at NLC spec beam densities with no sign of charge saturation. That's proceeding pretty well. Damping ring studies at ATF. You just heard a lot about that from the previous speaker, and highlighting this question that of whether intrabeam scattering is playing a critical role in what's going on here, and some need for further understanding, and then also the fact that multi-bunch beam dynamics is impacting the performance with multiple bunches. I'd like to highlight permanent magnet R&D because that's one of the things we've been pursuing at Fermilab in collaboration with Berkeley and with SLAC. And the idea here is to use permanent magnets to provide the focusing beam transport through the LINAC. The primary design criteria is these, because of the beam-based alignment, these quadrupoles have to be adjustable in strength. And when you change the strength, the magnetic center has to remain stable to 1 micron. And we're actually extremely close, which means within a factor of 1.5 to 2 of demonstrating this at the moment. Final focus and beam collimations being done both at SLAC and DAISY. You heard a little bit about this from Tom Markevich on the first day. There's optics designs and collimator wake field studies at ASSET. Then there's this LINKS proposal, which I'll show you a picture of in a moment, that may or may not be part of the future of this effort as a test facility. Finally, Livermore is taking the lead on trying to understand how to turn these linear colliders into gamma-gamma colliders. So there's IR design and laser prototyping going on out there. A quick slide on this LINKS proposal. What is it? It's a facility to provide E plus E minus collisions with 30 GeV per beam, about 50 nanometer beams. It's based on a reconfiguration of the optics of the SLC, where the SLD detector is. The goals I've listed here, and I've highlighted these first 2, which I think are the primary goals, and these would be secondary goals. I think the primary goal is, if one were to do this, would be to test some of the stabilization techniques that have been proposed for future linear colliders and demonstrate nanometer stability of colliding beams, and investigate some of the new optical techniques that are envisioned for controlling the beam and the background. And if one had such a facility, presumably there are other opportunities that would be opened up. Okay, let me move on to Tesla now for the next several minutes. The U.S. is actually in a unique position within the world in this business, because it appears that we're the only region in which the technology choice does not appear to be locked in. However, the character of the U.S. effort on Tesla is fundamentally different from the NLC program, because within Tesla the leadership comes from abroad, namely from DAISY. These are the 5 U.S. institutions who are members of the Tesla collaboration: Oregon, Cornell, Fermilab, JLab, and UCLA. And I would characterize the elements of the U.S. program at the moment as collaboration on construction, which is pretty much done, and operation of the Tesla test facility, which you heard described by the previous speaker. The U.S. did collaborate, these institutions, on the preparation of the Tesla proposal. Okay, I didn't run through the spell checker, sorry. Superconducting materials, processing and fabrication R&D is going on here, injector development and R&D. There's an engineering and cost study of the Tesla proposal, which is going on right now, involving these 5 institutions and SLAC, who's participating in this exercise. And of course, we are always day by day gaining operational experience with superconducting RF, both at Cornell and JLab, which presumably is relevant. Just a few highlights. I can't go through everything on that list. Again, if Hassan had put his transparencies from Frascati on the web, I would have had a nice picture, Maury. But anyway, there's fundamental investigations into breakdown phenomena and surface conditions and processing going on at Cornell. A lot of very nice work going on there. Flat beam studies at the Fermilab NICAD, which you now understand what it stands for, Photo Injector Laboratory, now called FNPL, previously known as A0 to a lot of people. This is a strict optical manipulation using quadrupoles and skew quadrupoles, which can change a round beam into a flat beam in theory. And here is a picture of it being done in practice. I've rotated this. This is vertical, this direction, horizontal, this direction. This picture was taken last November at FNPL, and the goal is to generate a flat beam with an emittance ratio tailored to a future linear collider, which is about a factor of 100 between the horizontal and vertical emittance. Typical emittance ratio achieved as far as 40, which is this picture. That's at 17 MeV and about a nanocoulomb bunch population. The promise of this is, of course, if one could fundamentally generate the correct beam emittance up front, maybe one could eliminate a damping ring, at least the electron damping ring. Next step here is to increase the emittance ratio by decreasing the space charge. And they are working on that. I will say that this particular enterprise, again, to give a little advertisement, is one that is starting to have significant university involvement from the universities. It's jointly run now by Fermilab and NIU. Okay, more highlights. There's this engineering cost study that we've undertaken with the U.S. institutions plus SLAC under Fermilab leadership. The goal here is to develop an understanding of the scope of what's actually included in the Tesla cost estimate. What isn't a goal, I always say when I give these talks, this is not an attempt to validate the Tesla cost estimate. Just to understand what's the scope of what's included there, what was the basis of the estimate and the estimating methodology. What sort of supporting studies in terms of industrialization schedules, fabrication, installation schedules, et cetera, gone into this? What are there either implicit or explicit implementation choices on some of the technologies? Which ones are important? Which ones need to revisit? Which ones aren't? And then finally, trying to map that onto a U.S.-style estimate. This exercise is being led by Peter Garbincius and Helen Edwards, and right now it looks like we will have a report available by mid to late February, which of course we expect is going to be public and shared with everybody. It's information that is applicable to and useful to everyone. Opportunities in the future. There are a lot of activities, as I said, centered at FNPL, many of which are also applicable to NLC. We'll continue the flat beam experiments. We've initiated some remote operations demonstration on this along with DAISY. We would like to start work on a third harmonic cavity to support longer bunches, and are looking. There's also a possibility of looking at polarized RF guns. Lay out a proposal, what's called Photo Injector 3. This would be an enhancement to this facility, which would utilize a Tesla-style cryo module and would generate a beam, electron beam of 100 plus MeV. And again, many of the local universities are interested in this, and there have been some meetings about, with some encouragement from Fermilab, actually generating a proposal from the local universities to undertake such a development. Engineering study of Tesla in a deep site, that's something I would sort of like to do. The deep sites tend to be quieter, as you saw earlier on, than the near surface sites, and there may that may have some implications on Tesla. And of course, there are a number of opportunities with other U.S. collaborators, which includes both labs and universities, that could be pursued. And again, I wanted to fit this on one slide, so I couldn't list those, but there are quite a number of other things people could look into. Okay, one slide on site investigations. We've been looking at sites both in Illinois and in California. This is representative of the California sites. Most of the California sites that are being looked at are northwest of Sacramento. This is Sacramento here. Here's the Bay Area here. This is a particular site they're looking at now, sort of up near Napa Valley. In general, these sites lie along this eastern ridge of the coastal range and tend to be sort of near-surface type sites. These are the two sort of specific sightings we've looked at in the northern Illinois area. One is called the north-south site. It traverses the Fermilab site, which is indicated here. As we looked at it, this particular implementation was put about 150 meters down in what's called the Galena Platteville dolomite, which is a very stable, very hard, good tunneling rock. There's over 100 miles of stormwater management tunnels in the Chicagoland area that have been created out of this rock. This, of course, is a more urbanized area than out here, so we've looked at this in a configuration in which all the injectors are on the Fermilab site, and so the off-site surface presence in this particular model is very low. It's limited to about 10 acres at each end of these two legs of the collider. If one goes west of Fermilab about 12 miles, one still does get out into farmland. This is a particular sighting we looked at that is south of DeKalb. DeKalb's right about there. We looked at this because it turns out there's a ComEd high voltage transmission line which travels east to west dead straight through farmland for about 50 kilometers out here. The advantage of the power line is not so much access to power, but we think it will tend to discourage developers from building houses in this vicinity, so we may not have to deal with that, and it'll remain farmland. But that's yeah, you can literally find a site that follows that line and doesn't hit a single house other than farmhouses. Okay, let me move on to sort of the last topic, which is what are the outstanding technological challenges. And of course, at this point, since I'm asked to give this talk, I get to express my own opinions, which is what these are. So I've tried to structure this the same way as I did at the beginning in terms of what we were trying to address. So let me go. I will go through it in the same order. Energy performance. Said there were structures and power generation. On the structures, I actually think it's safe to assume that both NLC and Tesla will demonstrate structures capable of supporting their design gradients. And again, here I put the loaded numbers, 50 and 24 megavolts per meter, respectively, over the next year. As you've seen, it looks like the X-band program is getting close to a solution, and the Tesla TTF, they have not been running at this sort of gradient, but they have a plan to demonstrate this over the next year or so also. I think the more critical issue that's going to take longer to work through is to develop and demonstrate the manufacturing methodology that could allow construction of the LINAC in a finite time for a finite cost. And of course, time is money, so those two statements are connected. And I think this is especially true in the case of NLC. Personally, I think the Tesla folks are ahead of the X-band folks in understanding how these structures are going to be built in industry. RF power generation and delivery. The NLC JLC RF distribution system has yet to be demonstrated. That picture I showed you. It's very clever, but it may not work. The fallback is a system similar to that was described in the 1996 ZDR that everybody believes probably would work, but it has the disadvantage of twice as many klystrons and modulators. There are alternative implementations that are being discussed, and I think they deserve continued consideration in parallel with trying to demonstrate this particular technology via the APAC test. Both NLC and Tesla have to develop and demonstrate industrial capability for delivering klystrons and modulators. I don't think anybody's done that yet. And the one thing that I wonder about is the multi-beam klystron, which is what's used in Tesla. Average tube lifetime needs some demonstration. We don't have much experience with that sort of technology operationally. Luminosity performance, there's a huge list of challenges here and lots of opportunities, so it's not possible to list them all. Again, a sampling that would fit on one slide. Sources, polarization. The electrons appear okay. What about positrons? We've had some discussion about potential utility of positrons from the experimenter's point of view. The flat beams, I think, needs to be further pursued. Damping rings. Damping ring performance specs, as we heard, still await demonstration at the ATF. Again, some of these issues we heard about in the previous talk. I think particular interbeam scattering, looking at that, lend themselves to experimenters and/or theorists getting involved. As we heard, it's just particle scattering. And again, at the coffee break, I would recommend. I met Sakazi Matwinga here for the first time in a decade at this conference, and he's the Matwinga of the Matwinga-Burricane formulation of interbeam scattering. So you might chat with him at the break as a university physicist who has contributed something to this field. The Tesla damping ring seems somewhat problematic due to issues related to its large circumference. Space charge as an example. It's I think the first electron ring that's ever really had a space charge potential problem. So there's some issues there. Emittance preservation, tolerances, alignment mechanisms, feedback algorithms all have to be defined in greater detail for both of these machines. IR feedback seems to be a viable concept for Tesla. NLC has adopted a similar scheme. Can it be validated? Is links necessary or desirable test bed for any of these things? I don't know if you're interested in that. You can talk to Tom Markevich or Andre Seri at the break. Reliability. We need a serious assessment of and a reliability model for these machines. I don't think there's been a lot of work on that so far. There are a lot of pieces to these things, and you'd like to have them up and running most of the time. Energy upgrades, 800 to 1,000 GeV range. NLC has a relatively clean vision of achieving 1 TeV based on doubling the length of the LINAC. Tesla has a vision of 800 GeV based on an RF power upgrade with a fixed length LINAC. So this means that the structures that you put in on day one have to be capable of supporting this 35 megavolts per meter if you can get the power to them. This has yet to be demonstrated, and it's likely before TTF2, which we heard is in this 2003-2004 timeframe. Beyond 1 TeV, possible paths for NLC and Tesla really have not been shown, and one should ask whether they exist. On the sites, we have to work on criteria, definitions, and then do site investigations and characterizations and try to close the loop between these two. And also, again, that the public and community relations is a very important part of this, again, as Maury indicated on Monday. And I think this is a case in which not necessarily the cold machine is ahead of the warm machine, but I think the German machine is ahead of the US machine. Finally, the cost really has to be ironclad, which has been alluded to before. Okay, so let me summarize what I think I tried to convince you of. The linear collider R&D is being pursued in the U.S. and abroad with the goal of establishing underlying technologies on this time frame of late 2003, 2004. Both NLC and Tesla are currently on paths that are expected to lead to credible technology demonstrations on this time scale. I will say that the current support levels in the U.S., and this means both people and dollars, and I think perhaps also abroad from what I see, could actually imperil this time scale. So people should not assume this is in the bag. So we need more resources, meaning people and dollars on this, and the experimental community can help by getting directly involved in the machine R&D and the technology discussion. Of course, if we are successful on the R&D and on establishing the public support and forming an international collaboration, the world could construct such a facility over something like the 2006-2012 time period and be operating and doing these experiments that we've heard about shortly thereafter. Last thing I wanted to leave you with was an advertisement for this workshop. I think Paul gave a list of upcoming workshops on the first day, and he neglected this one, which is the most upcoming one. This is the 9th International Workshop on Linear Colliders. This is primarily machine-focused. It's being held at SLAC, February 4 to 8th, so in several weeks from now. And I think if people really want to know, learn more about what's going on in the technology end, this would be a great opportunity. Here's the website. Thanks.
All right. We have time for a discussion again.
I would just recommend, as far as publicizing the sites where you want to have it, or at least your initial investigations of sites may probably be suppressed at this time, because you can't do anything but start to lose congressional support. I know my Southeast congressman would have looked at that and said, I have no interest in it since it's not, we don't have a chance of getting it.
Well, you know, we've talked about that quite a bit. We've been at Fermilab at least pretty careful at showing maps of Illinois or putting them on our websites. But on the other hand, you don't want to, get in a situation where you create the impression. I think most people believe this thing ought to be built near an existing laboratory, and you don't want to create the impression, I think, early on that everybody's open, and then you end up with the SSC phenomena where you had 50, hundreds of senators supporting the thing, which all of a sudden collapsed to 2, and so it sort of plays both ways.
Okay, I have another quick comment. There are a number of sort of radical experimental groups around the country that are playing with new technologies for accelerating gradients. And for instance, at Argonne, there's the Argonne Wakefield accelerator, and they're talking about soon reaching 100 megavolts per meter in sort of a radically different way. I mean, it might be wise to include them among the possibilities, at least, because I think it does two things. On the one hand, it increases the number of people who have bought into the linear collider, and on the other hand, a lot of these groups are struggling with small budgets, and it would help them to be sort of blessed by the linear collider movement, because who knows, in the second upgrade to the linear collider, you may use some of that radical technology.
There are other questions or comments?
I had a question since you brought it up. Are there any plans in the U.S. community to do any real R&D on polarized positron sources foreseen in the relatively near future?
Not that I know of. If someone else knows of something, they should say something for me.
We put in a proposal to the NSF to give us money to work on this problem. Alexander Mikhailichenko from Novosibirsk was sort of the inventor of a way of doing this, and we intend to pursue it.
The Tesla site was chosen carefully to allow for collisions between Tesla electrons and Hera protons. I can't see this with the two sites you consider at Fermilab. Is this to preclude this type of physics, or is this something which could change?
That certainly was not one of the criteria we established. Now presumably, if one were building a LINAC which traversed the Fermilab site, one could, jockey it around to potentially provide that capability. If one's going to build it out to the west, south of DeKalb, it seems pretty unlikely that one would then have whatever it is, a 30-kilometer transport line from DeKalb to Fermilab to collide with the Tevatron. Yeah.
Steve?
No.
The site to the west of Fermilab looks to be fairly far from the lab. How much more does that make it cost to build it there?
We haven't really assessed that at this point. I think the sort of discussion we have on is this a new site or is it an extension of the old site, et cetera, I'll tell you, the criteria I apply is, am I going to have to sell my house and move? And the answer is no, because it's only 10 miles away from the Fermilab site. I think in general, that's true. Most people work at Fermilab. In terms of how you would operate it, there's no reason you couldn't run that thing from the existing Fermilab control room. There's no reason that when things needed to be repaired, you couldn't bring them back to Fermilab and repair them and send them out there. Now, of course, there has to be some sort of crew on site there to just do the daily maintenance, let the people in, et cetera. There's an interesting report that was written by a committee, which I commend to you for reading, that was chaired by Ferdy Willicke, sponsored by ICFA, that actually addresses many of the issues of even more remote operations than this particular site right here.
If you end up with a cold machine, though, then you have cryo stuff at Fermilab.
You'd have to have the cryo plants out there. I mean, you're not going to go shipping cryogens 20 miles to the west.
Steve, does this photo injector lab that you described bear also on the problems of getting a positron damping ring, the issues that you referred to in your last slide?
No, it's not. There's nothing going on right there that bears directly on the positron damping ring. Whether that could evolve in the future, I don't know. It would depend on a good idea from somebody.
Are there any other questions? Okay, let's thank Steve again, and let's come back at 11 o'clock.